Alright, in this video, I'm going to show you how to plot isotherms of the SRK equation of state. So here is we're going to be using the generic equation of state and substituting in the values for the SRK equation, and then we'll use Plotly to plot these. So here I have some imports. These along with this line up here, this imported our CHE tools, and we'll use it to get the properties of water because we'll be plotting isotherms of water. And then these next, this is just, I imported NumPy and the tools that we need to graph. So let's start. So here's our equation that we will eventually need to plot. So we'll be holding temperature constant. So we need, and we'll input the specific volume, that'll be our independent variable, and pressure will be our dependent variable. So we need the constants B, which is the excluded volume, A, which is representative of the attractive force of those gas molecules, and epsilon and sigma. So I'm going to create a function. I'll call it SRK AB epsilon sigma, right? And what this is going to return is this is the function that will get A, B, epsilon, and sigma, right? So now we need to calculate those values. So if we scroll down here, SRK, we have our values for epsilon and sigma, so those are easy. So epsilon, I'll start with the epsilon. It is 1 for the SRK equation, and sigma is 0. Oh, I mixed that up. Sigma, oh no, sigma is 1, epsilon is 0. Okay, so all these other values are just for the other equations of state, so we could plot van der Waals equation, and in that case we would use 0 for both epsilon and sigma. So now let's calculate B, the excluded volume for the SRK equation of state. So B equals omega times gas constant R times our the critical temperature of water, which we can get using our CHE props, and that is divided by our critical pressure, which again we can get using our CHE properties. So now we need to define omega because this B equation has omega. So scroll down here again, we're going to use this table for SRK. This is the omega value. So omega equals 0.08664. Okay, now we have B, epsilon, and sigma. What's left is A. Left A for the last because it has the longest equation. This is our equation. So it is Greek letter psi times function alpha, which depends on the reduced temperature, and the and little omega, which is the eccentric factor, and then it's R, gas constant R squared times the critical temperature squared over the critical pressure. So let's type that. Psi times alpha times R squared times the critical temperature squared divided by our critical pressure. And this is all in parentheses. So now we need to calculate alpha and psi because we don't have those. So psi is equal to, we'll come back down to our table, and it's just a value. So for SRK, it is 0.42748, and alpha is, for SRK, is this equation right here. So you got to type that in, being extra careful. So the entire equation is squared, and now it's 1 plus 0.480 times plus 1.574, and we can get omega, which is the eccentric factor, using our CHE props. So that will just be times P dot W for omega minus 0.176 times omega squared. And then this will be times 1 minus the reduced temperature to the 1/2. So we have everything except the reduced temperature. The reduced temperature is the temperature of the substance over the critical temperature. So the reason this is used in the equations is it kind of gives a distance from the critical temperature that you are at a given temperature. And it's used in the equation because the farther you get away from the critical temperature, the more different your gas and liquid phases will act. So we will use our function to calculate A, B, E, and S at a specific temperature, so we need to pass temperature to it. And there we go. Run it. And this looks okay. So now if I pass a temperature to it, it gives us our value for A, B, epsilon, and sigma. So our next step is to actually calculate the pressure. So I'm going to come back up here to our generic equation of state, and I'm going to create another function, and I will call it SRKP because we'll be calculating the pressures using the SRK equation of state. And we need to pass it the excluded volume and our temperature, right? Because the excluded volume is the independent variable, and T will be held constant for our graphs. So now this is just going to return our equation. So R times T divided by the excluded volume minus the specific volume minus our excluded volume. And then we will subtract from that A divided by V plus epsilon B, also divided by V plus sigma times B. Right? So now we can use the function we just wrote because we need our A, B, E, and S values. So it will be A, B, E, and S will be equal to our function at that temperature. All right, and this will calculate our values, and there we have it. So now if I go and I want a pressure, let's say at a volume of 2 meters cubed, and temperature, we'll just go 500 again, it will give me that pressure. So now we can graph it, right? Because we have our pressures and we have our temperatures. So how we're going to graph this equation is we are going to graph it on a log scale. This is because the volume that a liquid takes up can vary greatly from the volume that a gas takes up, right? It can be, I don't know, 1 to 10 million, right? And so when we're graphing very long or very wide ranges in our graphs, we can graph on a log scale. That makes it easier to view, and that's what we want here. So what we're going to start is we need our specific volumes that we'll plot against, so we'll just call those V. And like I said, we'll use log space, so numpy log space. And how the function log space works is it is base 10. So if I put in a 0 as the starting point, it'll be 10 to the 0, so it'll start at 1. If I put in 1, it'll start at 10, right? put in 3, it'll start at 1,000. So we need to kind of figure out where we want to start graphing for our equation, right? And we want the smallest volume possible. And if you think about it, well, the smallest volume is 0, right? But if you try to compress gases down to 0, you can't, right? Each molecule has mass, and it is actually represented by our parameter B over here, right? It's the excluded volume. So the absolute smallest you can compress any gas is the excluded volume, because that's just the size of the atoms. If they were squished so tightly together that there is no room between the atoms or anything like that, right? So even if we start at B, if you look at our equation, we'll get 0 in the denominator, right? Because if V equals B, we'll have B minus B, and that's 0 in the denominator, which is undefined. So what I'm going to do for graphing is I'm going to start at, this is 1% over B, right? And we need to remember that we're graphing on a log scale, so let's just take the log of that. So we'll use numpy log 10 of B, of 1% of our excluded volume, and then our end value will be, we'll just go up to 10. We'll see how that looks. We might to shorten it down, and we'll do 400 points, whatever. And so now we need to define B, which we already defined up here in our code. So I'm just going to grab that. This is B, and here is the value for omega. Right? Now let's create our, we need our pressures, right? We need to calculate the pressures. So our pressures will be equal to our function we created to calculate pressures at V, which we created, and our temperature. So we're just going to start with 1. So we'll have our temperature at 500. So V comma T, right? And then we can do figure 1. We'll make our graph. And then we'll add this curve to our graph. So we'll add scatter. Our X is going to be our specific volumes. Y will be P. And then I'm going to update the x-axis and make it on a log scale, right? Because as we said, we calculated our specific volumes out, logarithmically spaced, if you could say that, and so we need our axis to reflect that. If you try to graph it without doing this, it just looks awful, right? You'll get a line straight down and then straight across, and it really won't work out as you like. So our type will be log. So let's see. There you go. So like I said, I mean, it's still straight down and over, but this is for a different reason. This is because our range is too high, right? So we need to update the y-axis and set a range for that. Update y-axis. Our range will be, we'll go 0 to, let's go to 1 billion, right? Because we have 15 billion up there, and just kind of see how it looks, right? Still not quite, and it actually looks like we need to go below 0, and we're still a little too high. So let's bump that down by a power of 10, and what do we want to graph for our lower range? Let's try -1. We'll go -1 million. Try that. Well, so it's getting better. We actually have a wiggle, but it's not quite there, so we still need to lower this by a little bit. Let's try to bump it another power of 10. Not quite there. Do another power of 10. And there we go. That looks pretty good. there's our first isotherm. So now I'm going to go back up, and we need to graph quite a few of these, right? So to do that, we're going to use a for loop. So we're not going to graph just one anymore, right? And we're not just going to have one temperature or one set of pressures. So we are going to use a for loop. So for each temperature, we'll create a range of temperatures. Our start, so the lowest we can start is 273 Kelvin, right? Because below that, water's frozen, so there will be no, you can't really change the volume, right? Doesn't make too much sense. So I'll start just above that, and we'll stop, I don't know, let's go to 700, and our step, let's do it by 25, right? And so then we will have our figure 1, we'll add scatter, right? X equals our V, which we calculated above, and Y equals, we need our pressure, right? So I'm going to add into a line that calculates the pressure for each temperature as we go through the loop, right? So again, we'll use our SRK pressure function, and it will have V and the temperature given. So now we have P. We can graph pressure, and I'm going to go ahead and name these as we go along so we can kind of see the colors and see which curve corresponds to which color. So our name will equal to the temperature, and we will actually print the temperature. So we'll cast it to a string and print that, and we'll go ahead and see how that looks. There we go. So we need to adjust our scale a little bit. We're going out way too far to the right. But if we zoom in here, you can see the isotherms, right? So I'm going to kind of edit the range of this. How far do we want to go out? Go 1E. We'll try this. And actually, we know our starting point, which is right here. And our ending point will go to, let's go to 0.1. We'll go to 0.01 and see how that looks. There we go. A little better, still not quite the best. I can play with the range a little bit to make it look neater, but there is our isotherms, right? If we zoom in, it's a little clearer, and you can see the different curves.